Welcome to the session about resolution and texture loss. So I'm going to introduce you to the core methods that we use for measuring resolution and the spatial frequency response and the differences between these methods. First of all, some clarification about the term. So resolution is not pixel count. At least to our definition, we say that the amount of pixel is not necessarily related to the resolution. And resolution is the level of details that you have in an image. So we try to make a difference between pixel count and resolution. Another aspect that you actually measure with an SFR is the contrast. So that is basically the reproduction of lower or medium frequencies, and yeah, that can also be measured with an SFR. The contrast can be enhanced by sharpening. So you see here in this example, I think you can clearly see on the right, the image appears sharper, so the subjective impression of sharpness is higher, but that does not come for free. So if we zoom into the image, we can see that the image on the right actually has some artifacts there, so strong sharpening artifacts, and that is of course an issue. So sharpening means you need to find a good trade-off between the right amount of sharpening for a pleasing image, but not too much for an annoying image. Another aspect that I'm going to talk about is the texture loss, so the loss of low contrast fine details, seen here like in the fur of the teddy bear or in the wooden structure of the toy. Okay, which methods do we actually have to measure resolution? So the first one that I want to talk to you about is the SSFR method that uses the Siemens star. So the device in the test reproduces a sinusoidal Siemens star. So if you look over the radius, it's not black and white, but it's a sine wave. And that is a core property of these test targets. It was actually developed in here at Image Engineering, and the ISO technical committee picked it up later on, so it became ISO standard. The core idea is that you can read out the harmonic function. And if you go into the signal theory, you know that if you feed in a harmonic function into a linear system, you will also get a harmonic function out, just change in its phase and in its amplitude. So as the amplitude, we can also see as modulation. So we can directly measure the modulation from the harmonic Siemens star. So the core idea is we detect the center of the star and then we read out the digital values over the radius. If we have done that, we can fit in a harmonic function. So a harmonic function that minimizes the error. And if we have that, we can calculate the modulation from that. So we have the modulation and we know the radius. The radius can be calculated into a spatial frequency. That means if we measure for all different radii, we can then also measure for different, or we have the measure for different frequencies. So that gives us now our MTF or SFR. The nice thing about the Siemens star is that we can actually measure in all orientations. So you see here we have horizontal, so 8 segments. Segment 1 and 5, 3 and 7 can measure horizontal and vertical, but we also have 2, 4, 6 and 8, so that measures in the diagonal. So a lot of properties of lenses are depending on the orientation. And with the Siemens star, we measure all of them at once. An example here from a TE268, so a very robust test target, where you have 25 Siemens stars. So this target is used a lot for lens assessment, lens testing. So this image was captured and now analyzed with the IQ Analyzer software. And in this overview plot, you can see quite nicely that on the left side of the image, we have a problem. So the black circle represents the theoretical maximum of the device, depending on the pixel count of the sensor. And the white polygon on it represents the measured limiting resolution per segment. So the more the white covers the black, the better. And we see on the left side that there is an issue. But we can also see from the orientation that there is differences in sagittal and tangential orientation. So you see you can learn a lot just from a single image analyzed with the IQ Analyzer here. Okay, another method that we have is the ESFR, sorry for that, is the ESFR method. So that is the slanted edge method. So it is relatively simple in terms of targets. You just need slanted edges in the target, and then you can analyze these. The core idea is that you have, or first measure the edge spread function. So drawn here in blue, the ideal. So an ideal camera would be that you have the low signal and then you jump to the high signal. And that gives you the, or that represents the ideal edge spread function. Of course, a real camera would not do that perfectly. It will, wash out the edge a little bit. So that is what we actually measure here, shown in red. So the derivative of the edge spread function is the line spread function. And the line spread function for the ideal camera would look like an impulse, as the derivative of a jump is an impulse. And for the real camera, it has more like a bell shape kind of thing. And then the Fourier transformation of the line spread function gives you the spatial frequency response. And the ideal again would be a constant, so the Fourier transformation of an impulse is a constant, so the SFR would be perfect, but of course for the real we have our SFR shape there. So that is how the core algorithm of the slanted edge method. The interesting and the tricky thing about it is how to obtain the edge spread function. For that, there is an algorithm that projects all pixels along the edge into bins. And the bins can be the quarter of the size of a pixel, so that we get a 4 times oversampling with this process. So the first we detect the edge, then we project all pixels into these bins and can work with them. We have to be a little bit careful about the angle. So the angle of the edge in the image defines how the pixels are distributed in the different bins. So it does work for many angles, but for example, it does not work with 0 or 90 degree, as we would not be able to fill the bins with pixel values. So you have to be careful there. Also 45 degree might be a problem. Okay, if we have measured the edge spread function in great detail, what we can also use that for is that we measure the undershoot and overshoot. So I draw the real camera in the other slide without any kind of sharpening. But in reality, with many devices like mobile phones, security cameras, everywhere where you have some sharpening applied, and your edge spread function might look like this, where you have a strong overshoot and undershoot, or like ringing artifacts. So these can be disturbing depending on size and amount, and this is definitely something that you want to measure, that you want to track in your development phase. Here also an example how this can be useful. So we compare a Nikon and a Canon camera with how the different amount of sharpening measures different amount of sharpening. So we set different sharpening level in the camera and see what sharpening did we measure in a test target on a high contrast and on a low contrast edge. And we see that the Nikon has very similar results for high contrast and low contrast, while the Canon makes a huge difference between high contrast and low contrast edge. So with this simple measurement, so just a bunch of images, we can learn about the image processing of this camera. So if you want to learn from your own device, or maybe from the competition, these are very useful tools to do this. Another method that also plays great into this range of resolution measurement is the dead leaves. And I'm going to show you dead leaves mainly is the name of the pattern, and then we have the dead leaves analysis, like dead leaves cross or dead leaves direct on top of this pattern. So this method mainly is addressing about the texture loss, so the loss of low contrast fine details, which we cannot see that great in cement stars or in edges, so that's why we needed a new method. The dead leaves is not new, so the structure itself was introduced 2001, and it was first introduced into the community of image quality testing in 2009. and developed over the years. And the biggest step into a robust and reliable measurement was the introduction of dead leaves cross method by Kirk, so Leonie Kirk, a master student at image engineering at that time, that developed a method to measure the SFR on a dead leaves pattern in a complete new way, which showed to be very robust and extremely powerful. The original idea of the dead leaves measurement was that you reproduce a target with your camera, and that gives you the image. So in terms of signal theory, you can say we have our target spectrum, that is x of f, we have our transfer function h of f, and we have the image power spectrum y of f. So if we can measure the power spectrum in the image, and the nice property about the dead leaf structure is that we can describe or model the power spectrum just by the knowledge of some properties of the chart. So as we know power spectrum image and power spectrum target, we can calculate the h of f, or the SFR in between. So that's the fundamental approach that was first taken in 2009 when it was first introduced. Problem there was highly influenced by noise. So you see some examples here. A lot of noise on the image will render your results useless. So McElwain et al. Presented 2010 a modification to that. This is what we call now dead leaves direct, where you do not reproduce only the dead leaves pattern, but also a gray patch. And from the gray patch, we measure the power spectrum to correct or to optimize the power spectrum of the image. That works quite well, but has still some remaining So one remaining problem, even with the dead leaves direct, is that we actually only measure the amplitude response. What does that mean? So basically everything that is on top of the dead leaves pattern in terms of like noise or other artifacts will be also introduced into the or will be also added to the results. So we are highly influenced by noise, and by correcting that with a gray patch does not the whole job, because removing noise on a gray flat area is a very simple task for noise reduction, but it will not do the same on the complex structure of dead leaves. So that's why the dead leaves direct is a great improvement over the dead leaves core method that was first introduced, but it still has problems. So that's why the dead leaves cross was introduced, where we use the cross power spectrum of input and output. Sounds complicated, but I mean the algorithm is presented in a paper you can then just download from a website. And there you have the benefit, you have the full transfer function. That means we have phase and amplitude, and we can use the phase to differentiate between information that came from the target itself and information that is just noise. And therefore we have a much more have a method that is more robust against influences of noise. So in the calculation, you have a two-dimensional transfer function, and then we can take the real part of it and make it to a one-dimensional, and that gives us the SFR. So the examples you have seen before, this was the old approach, and this is the new. So you see much more intuitive, correct results with the dead leaves cross method. Also here some examples for a mobile phone camera. On the right, captured under bright light. On the left, the same target, same position in the image, just captured under low light, in terms of 1000 lux versus 60 lux. What you can see is that you clearly have a loss of details in the dead leaf structure. But if you have a look at the marker, so the black and white marker in the corners, they look nearly the same. So that's another indication that the slanted edge method or high contrast edges do not work well to describe texture loss. Same high contrast target, same camera, same lighting conditions, same effect. So we see a loss of details while the edges remain the same. And these are the results or the SFR plots for the images that you have seen before. So these results match quite well the visual impression, so that we can differentiate between these devices. As said, the algorithm itself is presented in a paper published at Electronic Imaging, and you can just also go to our website, Image Engineering, .de or .com and go into the library and then download that paper if you want to see that in more greater detail. What is of course interesting, now I introduced to you the Siemens star method, the slanted edge method, and the dead leaves, all gives you an SFR. And what are the differences actually, and when do I use which? So already as a beginning, our recommendation is use all of them. And that's the pure reason for that is all have advantages and maybe some disadvantages, and they all tell you different things. So, for example, here we have a T42 multi-pose test target where we have dead leaves pattern in 2 different contrast level, we have slanted edges in 2 different contrast level, and we have a Siemens star. If we take raw data, we can see we nearly get the same results. So raw data, no processing, it doesn't really matter. So there you can use all of them. But if we have a fully processed image, and there we actually do get differences. So here the example of a camera where we switch between 0 sharpening, default sharpening, and high amount of sharpening. And from the differences, we can tell about the processing in the camera, so that we have so here we can tell from the very high response on the edge, we can see that we have strong sharpening. From the shape of or difference from Siemens star to the dead leaves, we can see that we have significant texture loss, and so on, so on. So this is very powerful. So if we compare these, we say that we can use the Siemens star as a robust method to measure the optical performance, because as you have seen, we can measure in many different directions and we get assessment of the optical performance. While the slanted edge we use for the assessment of the signal processing, particularly of sharpening. And the dead leaves is a very powerful tool to measure the texture loss. Of course, and in terms of like chart design, the slanted edge is very flexible to do chart layout. So like on production line environment where you have huge control over the camera about the images and the processing, slanted edge might be the choice because it's easy to design, to implement, it's fast. While when you really want to analyze the camera and the signal processing, then like dead leaves and Siemens star are definitely your choice. Of course, there's always some disadvantages maybe. So for example, the Siemens star, it's hard to align it for high field of view cameras or for cameras with strong distortions. So you might not be that flexible with the chart layout, and you cannot produce it in all flavors as you would like. Also, that distortions can be a problem for the dead leaves target, as we need to match image pixel with reference pixels. So, but also, and another disadvantage of the slanted edges, as said, that it's highly influenced by sharpening. So it might be a problem if you don't have raw data. So thanks a lot for watching this part about resolution. Of course, this could only be your high-level overview. There's a lot of more details in our trainings, and if there are questions, please let us know. And for now, thanks for watching.